Alright guys, so we had left off, and I know it's been break. Remember, you got those videos you can go back and watch if you need to. So before we went into break, we had just barely introduced. I introduced some confusing topics for you, and hopefully you guys are good with those now. Watch those videos a couple times to get that. But this right here is kind of where we left off. Was we just introduced the 4 quantum numbers. I never told you anything else besides their names and abbreviations for them. But today I really want to focus in on these quantum numbers and focus in on how we will use them. So within this, we're going to start off, and I'm going to start talking about the first 3 quantum numbers. Okay, I will add the 4th one, but I need this little bit of board space over here, is why I've left that blank. I will talk about the spin quantum number a little bit, but these are the 3 that comes from Schrodinger's equation. First we have the principal quantum number, then we have the angular momentum quantum number, and third and last we have the magnetic quantum number, and those are the 3 that comes from Schrodinger's equation. So within this, what I want to do is I want to talk to you about these and show you what information you can actually gain from them. So the first thing we're going to look at here is the abbreviation of these guys. So the abbreviation of the principal quantum number, all it is a lowercase n. This should look familiar to you. So it's just a lowercase n. This should look familiar to you because I told you when we were doing those electron configurations that N was our energy level. So that's preceding us a little bit of what it will tell us. So N will tell us the energy level. So the principal quantum number will tell us the energy level we're looking at. Now this is the big thing where I'm saying you've seen this before. I looked at you and I told you, remember when we talked about S, P, D, and F, and I was telling you about whenever we were trying to find the rho for those electron configurations. So we looked at S, the P, the D, and the F. We looked at these subshells. And what did I tell you? I told you that rho for S was equal to N. Rho for P equal to, well, I got backwards. I'm flipping it in my head because we're going to flip it today. Told you N equals rho for S. N equals rho for P. But for D, N was equal to rho minus 1. For F, N was equal to rho minus 2. This right here, this N, is what we're talking about here. That is the principal quantum number we were looking at. So it will tell us the energy level, but other things it can do is show us, in my purple marker, it'll show us the rho for the element off the periodic table. That'll make sense here later on when we actually start using these, and I'll show you how we're going to use this information. It shows the rho from periodic, I'm just going to put PT from the periodic table. Okay, that PT stands for periodic table because I don't got a whole lot of room to deal with this. Alright? How can we do this? Because it works backwards as well. Remember in math, whenever you're looking at an equation and you're looking at a statement, the equal signs mean the left is equal to the right. So if I know what N is, then I know what my rho is. Now we need some more information, and I'll show you a pattern of how we're going to figure that out. But this is what we're looking at. So the principal quantum number has the abbreviation of N. It will tell us the energy level. There's another piece of information it will show us. It's called the shell. Okay, it tells us the shell I want to use that terminology in case when you get to college they use that terminology. Anymore we kind of see it going away a little bit, but it's still there because this is kind of like how it looks. So remember back to like Bohr's model. So we have that nucleus with the proton, then we have the first energy level, second energy level, third energy level. Whenever you've seen those ends there, that's what it was talking about. This is telling you the shell. This is what it's talking about. So like 1 is this area in here. 2 is this area in here. 3 is this area in here. It tells you what part of the whole atom that we're looking at. Alright? Remember, these 4 quantum numbers work like zip codes. These are locations for these electrons. Alright? So I want to talk about the principal quantum number just a little more. So the principal quantum number, let's do, abbreviated as N, okay? It can have a possible range. So the range that it can be is from 1 to 7. The range has to be a whole number. And what that's saying is it can't be 1.1, 1.2. Remember when we talked about those energy, with within these levels, it's like the salty spittoon. You ain't getting in there unless you're this tough. Okay, you gotta have muscles on your muscles. Gotta be muscles on your eyeballs. You gotta be able to eat a bowl of nails without any milk. Okay, that's what this is. Like the only way you're getting to this level is to have this much energy. If you're almost there, you still can't get into that energy level. It has to be a whole number. Okay? It cannot change that. The lowest number N can be is 1. The highest number N can be is 7. And it has got to be a whole energy level. Alright? If you guys got any questions, please, please, please let me know. So I will go on and tell you there is a simple way, they define it as a simple way to figure this out. If you're trying to figure out how many electrons can go within a shell, then what you can do is there's an equation of 2n squared. So you just fill in for n, do that mathematical property, and you'll figure it out. I'm not huge on that. I really don't focus on that a lot. But I do want to make sure you are aware of that and that you know. So now we're going to move on. We're going to move from the principal quantum number, and we're going to move into the angular momentum quantum number. I always get tongue-tied a lot on this one. The angular momentum quantum number. Within this, the angular momentum quantum number, it has an abbreviation, and its abbreviation is a lowercase cursive L. So I will look at you and tell you, like on problems and stuff that I give you guys, I don't have the ability to make that cursive on my documents. If there's a way, I don't know how, and I'm not caught up with it, I'll go on and tell you that I will do just like a straight L, and just know that that's what that's talking about, is that angular momentum quantum number. So within this, the angular momentum quantum number is very, very specific. It's the one that, this is where stuff starts making sense for you guys. This is the one that it will tell you the shape of the subshell. Okay? So it tells us the subshell. You say, Mr. Hall, what do you mean the subshell? This is what I mean. You've heard of them before. S, P, D, or F. That's the subshell I'm talking about. This is the number that will identify it for you and tell you what you're dealing with. In this, it will show us, the subshell, but the thing it'll show us is what block off the periodic table. So the block from the periodic table. So in this is going to give you the block. Now I know that seems like we haven't done a lot with it, but start piecing some stuff together. This number gives me the block from the periodic table if I'm in the SP, D, or F block. And this number, principal quantum number, tells me the rows. So it really narrows stuff down for us. In this, the angular momentum quantum number also has a range. And here's the thing that you need to know. It's set. S, P, D, and F. So S, P, D, F. Whenever you're looking at these, and it's a set defined number. For S, the number is 0. For P, the number is 1. For D, the number is 2. For F, the number is 3. This is one of those you just get it. You got to accept it, and you just walk on and go on through life. This is defined. Whenever we start working problems, whenever we start working through these things, this right here is the piece of information every year I have students struggle the most with. So, have this information, write it down. If you're ever doing anything with the quantum numbers, write that down. Because you're automatically going to look and say, wait, why is it this? That's because S is 0, P is 1, D is 2, F is 3. Now if you're looking at a possible range, this is where the range for L comes, for the angular momentum quantum number comes in. So the range will always be defined to be from 0 to n minus 1. Now here's the thing. These are two separate pieces of information. You're going to use this piece of information in one case, you use this piece of information in one case. Here in a little bit what we're going to start doing is first you're going to determine if a set of quantum numbers can exist. And from that, that's where all these ranges that I'm telling you come into place at. This is where the range happens. Now, the other set of questions you're going to do is first you're going to give me the 4 quantum numbers for an element off the periodic table, and you'll do vice versa. For an element off the periodic table, you give me the 4 quantum numbers. In that case, you'll use this piece of information. That's where these things separate out. Okay? Once we work these problems, it'll make some more sense. Don't freak out too much about it. But pretty much that's the range. So here's where all this information comes into play. If I looked at you and I told you the principal quantum number, n, was 3. The question then to that would be, could L be 3? So n is 3, can L be 3? The answer is no. That can't exist. Why? Because the range for L is from 0 to n minus 1. So what can L be? L can be 0, 1, or 2. This one also is a whole number. The reason the L is a whole number is because it's based off n, which was a whole number. So it must also be a whole number, which you will find out all of them except for the spin quantum number is a whole number. So this is your range. This is what you're looking at, okay? Determining if things can exist or not. For this, for example, if I looked at you and I asked you what was the angular momentum quantum number for the element, for the last electron and the element carbon. where's carbon at? Carbon's in the P block, right? You should have the periodic table in front of you. It's in the P block. P, what is L then? It's 1. It's that simple. Okay? So that's the angular momentum quantum number. Please, 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 if you have questions, let me know. I will look at you and tell you in this that this tell us the shape as well. So within this, the angular momentum quantum number not only tells us the subshell, but it also tells us the shape, which is kind of telling it with the SPD or F. So and shape, and every one of those have different shapes. So S is kind of like a sphere, it's kind of like a ball, like a basketball. P is kind of like a peanut. The D, those are where things get complicated. They're very different. They are, they're just interesting, say it that way. Some people like to call it dumbbells. I don't think it really, like it's shape-wise, I don't know if it really fits that. You just need to look these images up and you'll see what I'm talking about. And then when you get to F, they like to say fancy, I say freaky, because those are shapes that you're like, I didn't even know that shape could exist, kind of thing. So that's what you're looking at here with the angular momentum quantum number, okay? I do encourage you to look those images up. I'm not going to require you to memorize what those images look like, because that is not what's important to us. Okay? So now we move to the third number from the Schrodinger's equation, the magnetic quantum number. Hopefully you guys remember the magnetic quantum number. Within this, the magnetic quantum number has an abbreviation of a lowercase m sub cursive L. You're going to see why there's that sub cursive L. If you haven't figured out the pattern, this number was dependent on that number. This number is dependent on this number. The ranges is what I'm talking about in that terms. But what you'll see here, that's the abbreviation of it. So within this, we can get some information from this. Okay, so what does this number tell us? The magnetic quantum number tells us how many orbitals there are. How many orbitals? It also tells us the orientation. So it will tell us the orientation of that orbital. This is where things are going to start making sense. Okay, this is where hopefully things will start to click. When I'm talking with orientation there, so you all have seen a Cartesian system. That was awful. Man, you can tell I've been on break. So we've all seen a Cartesian system like this before. So I'm going to use P as an example because that's where it gets simple and easy. Once you get in the D, it just gets hard. So in this, for example, what axis is that setting on? That's clearly setting on the x-axis. What axis is this setting on? That's clearly setting on the y-axis. Now the last one's not as obvious to you guys because I don't think you guys have ever done this in your algebra classes yet. But this is 2D. But if we're going to go to 3D, there's actually an axis that comes out this way as well. So that axis is coming out from the board and going behind the board. And that's going to be the next letter in the alphabet, Z. That's the Z-axis. So what we're seeing here is the X, Y, and Z-axis. This will tell us the orientation. Here's the first orientation There's the first orbital's orientation, the second orbital's orientation, and the third orbital's orientation. You go, hold up, wait a minute, what do you mean? Okay, what am I dealing with? What did I tell you I was going to be dealing with here? A P, right? So I'm dealing with a P subshell. Whenever you looked at P, how many dashes did we put for P? 3. 1, 2, 3. So let's just say we're in the 2P. So this is what I did. I told you to label in the middle. I did that to keep things simple for you. Because in reality, this is 2px, this is 2py, this is 2pz. This is an orbital, that's an orbital, and that's an orbital. Go back and look. I told you. How many orbitals? I need some room here. Okay, which grade? How many orbitals does an S have? One orbital. Because there's one shape. There was one dash. P, how many? 3 orbitals. D, how many? 5. F, how many? That was 7. That's how many orbitals are within those subshells. That's what we're seeing and what we're dealing with. This is where things get tricky though. And this is where I'm going to look at you and tell you, we're not going to use X, Y, and Z to this. Okay, that's going to change out because when you get into D, then mathematically it's not as simple as A, B, C, D, E. It's like X, Y minus Z, X. And you got X, Y squared minus Y, Z to the third. Stuff like that. And, you don't need to know that. I'm just looking to see, you know, how many orbitals there are. We're keeping this very simplistic. Remember, this is the basis and background for quantum mechanics. We don't need to make this complex. It's complex on its own. So in this, that's what we can see. This is what this number will tell us. How many orbitals, how many orbitals, and the orientation. Now within this, what will it show us? This is where we start getting a full picture. It shows us the column from the periodic table. Well, columns. It'll narrow it down to the columns from the periodic table. I promise you this will make sense in a little bit. Just give me some time, okay? Just get these notes down. And I go over there to the periodic table. That's where it'll click and start making sense. So these are the columns from the periodic table. So whenever you're looking at this will narrow us down to the columns. So look at it this way. What's this number give you? The block. So we have the block. This number shows me the row. So now I have the row of a block narrowed down. This narrows me down to the columns. So now I've took it and narrowed it all the way down to 2 options for what the element is. Okay? In this also has a range. So M sub L has a range. The range goes from negative L to positive L. This is where that little subscript comes in to remind you that this number is dependent on that. This number depends on this number. So in this, let's say for example, let's do N as 4, L, I'm going to do L as 3. So that means M sub L. What can M sub L be? That's where the range comes in. So right here, we're looking at L is 3. So from negative L, negative 3, to positive L. Positive 3. Now this is the thing. This was a whole number. This number based off that. So this number was a whole number. This number can only be a whole number because this number is based on that number. Hopefully that makes sense to you. And you get that it can be negative 3, negative 2, negative 1, 0, 1, 2, 3. That's the possibility for this. That number, M sub L, can only fall within that range. It cannot exceed that range. So in this case, if I wanted to put negative 2 down here, this can exist. That's what I'm saying. That's the range for this.
Sorry for the interruption. I need to see all senior teachers. Any teacher that teaches seniors will need to see me tomorrow morning at 8 o'clock. First thing in the cafeteria. Thank you.
So within this is the possibility. This is the possible range of it. Alright? So we can go into that range. We cannot exceed that. So if this was negative 4, those set of numbers could not exist. That's what I'm saying. Okay? All of these numbers are dependent upon one another. This is why I didn't include the spin quantum number in here. These three numbers come from the Schrodinger's equation. But remember, there is a fourth quantum number. So think about it. With this information we have, off the periodic table, we narrowed it down to 2 options. So now we need a fourth piece of information to narrow it completely down. And that's where the spin quantum number comes in. So our spin quantum number. The spin quantum number, you guys see the abbreviation in case you don't remember it. The abbreviation is M sub S. Here's the important thing of what it will tell us. It will tell the spin of the electron. This is where this number comes in so important. So you're setting 2 things that are the same charge within the same area. What happens to like charges? What do? They repel, right? They want to push away. How can we get these electrons to stick in there? Then this is what happens. One electron will spin, in simplistic terms, will spin this way. It'll spin counterclockwise, while the other one spins clockwise. So what's happening are they're spinning in opposite directions. When you take something electrical and spin it, what happens is you create a magnetic field. So now there's a magnetic force that gets introduced, and the magnetic force is attractive, so it'll cancel the repulsive force of the like charges out to keep the electrons in there. Now here's the really cool thing. This is what's really cool. Quantum entanglement. And there were some professors and researchers at, I want to say it was Berkeley University, and there was another smaller university in California that decided to test this to see if it was proven. So they had separated out 2 electrons. They knew the spin of those electrons when it first started. What they did is at Berkeley, they flipped and changed the spin of the one electron. They did nothing but observe the other electron at the other university. And here's where the interesting thing takes place. when the one electron was changed to where it spun in a different direction, the other one flipped at the same exact time to where it would spin at the same exact time, to where they're entangled. This is where we get quantum entanglement. This is what helps overcome all that. They are entangled. These electrons are entangled together. They cannot be separated. I know it's one of the weirdest, freaky things on the face of the planet. I get it. Trust me. Anybody that deals with this will look at you and tell you it is. But they get an enjoyment out of it being weird and freaky because everyone's like, wait, what? And they're like, yeah, I know. It's freaky, right? Okay? This actually happens, though. Now, this is what it will show us. It shows the element from the periodic table. All right? That's what this thing will do. It's going to actually show the element from the periodic table because we had it narrowed down to 2 columns. And you're going to see here in a minute how it separates out. And we'll break it down. Okay? Before I start jumping in and breaking down the periodic table, I actually want to start getting you accustomed to how these numbers are going to look and how answers and things will come about. Alright? So this is what we're going to do. We're going to erase all this, and then we're going to start working with these numbers actually. Okay? And again, if you guys got any questions, just ask me. And I gotta be honest, I'm excited for you guys to get to come back. Finally going to get to come back, but then we also have the issue going on with, none of y'all have asked me any questions, and typically I'm bombarded with questions. So hopefully you're getting all this, because remember, this class links together, and I am moving on with things, so whenever we do come back in person, I'm going to move on. I'm not going to go back and reteach this stuff. Alright? So this is what we're looking at. We're just looking at a set of numbers. Principal quantum number, angular momentum quantum number, magnetic quantum number, and the spin quantum number. Oh, snap. I meant to tell you, spin quantum number can only be plus 1/2 or negative 1/2. I'm so sorry, I should have added that. Go back and add that. But it can only be plus 1/2 or negative 1/2. It cannot change. That is the set numbers. It will not be anything else. That's what it is. It is set to that. It's defined to that. Bada boom, bada bing. That's what you're looking at. Okay? Plus 1/2, negative 1/2. Now, jumping into this, I'm just going to throw some sets of numbers up here, and I'm just literally going to go across the board. I'll do different colors so you don't get confused. So, alright, so if you need to, pause it real quick and get these numbers down. But I'm just going to start rolling through. So this is what we do. We look and see, can these numbers exist? So this is what I would ask you. Can these set of quantum numbers exist? Yes or no? Alright, and I'm going to go the extra mile today, and I'm actually going to point out where to as the problem is. So in this case, we're going to start here. So let's look at n. n is 1. Can n be 1? Yes. Why can n be 1? Because n has to be a whole number between the numbers of 1 to 7. It fits that bill. L. L is 0. Can L be 0? In this case, yes. Why can L be 0? It's because L is from 0 to n minus 1. n is 1, so 1 minus 1 is 0, so the only number L can be in this case is 0. M sub L can only be from negative L to positive L. So what's L? L is 0. That means it can only be from 0. So it can be that. The spin quantum number can only be plus 1/2 or negative 1/2. This is negative 1/2, so it's good. This number can exist. So let's go to the orange set of numbers. So the first one, n, principal quantum number, is 4. Can n be 4? Yes, because it has to be from 1 to 7. So that's good. L, m sub L is 5. Can m sub L be 5? Well, look at it. It can go from 0 to n minus 1. n is 4. 4 minus 1 is 3, so it has to fall in the whole number range between 0 to 3. This is 5, so no, this cannot exist. So that set of numbers can exist. Notice I didn't go any farther than this. When you're checking these numbers, this is how you do it. Just start from the top, work your way down. It's that simple. So let's look here. So n, let's look at the black. N is 6. So can n be 6? Yes, because it goes from a range of 1 to 7. Whole number, so 6 falls in that, we're good. L, alright, in this case, L is 5. So L is a range of 0 to n minus 1. In this case, n is 6. 6 minus 1 is 5, so we can go 0 to 5. 5 fits the number. M sub L, that is in a range of negative L to positive L. In this case, negative L is negative 5, positive L, positive 5. So between negative 5 and positive 5, negative 4 fits the bill. So that can exist. Let's look at the spin quantum number. The spin quantum number can only be plus 1/2 or negative 1/2. Negative 1/2, we're good. This can exist. Alright, let's look at the number, set of numbers in red. So we're going to start off. N is 8. Can the principal quantum number be 8? Hopefully you're screaming no right now, because n can never be 8. It can only be from 1 to 7. That's where we stand right now within science. Wait, I mean an X on that. I don't mean a check. What am I doing? That cannot exist. Because n can only be from 1 to 7. So that exceeds, 8's greater than 7, it exceeds it. So it cannot exist. Let's look at the last set of numbers. Okay, the ones in green. N is 4. Can n be 4? It's between 1 or 7. It's a whole number. Yes. Let's look at the angular momentum quantum number. L. L is 3. Does that fall between 0 to n minus 1? Yes, so that can also exist. Now let's look at the magnetic quantum number, m sub L. M sub L is 2. Does that fall between negative L to positive L? And the answer is yes, it does. So that can exist. And this number is here just to prove to you, check everything. Don't just assume something's going to be right. The spin quantum number can only be plus 1/2 or negative 1/2, and I have negative 1/4. This cannot exist. I know what you're thinking, Mr. Hall, you're evil and cruel. What if you put negative 2/4 there? I won't do that, as I'm not worried about you simplifying a fraction. That is not what I'm concerned with or worried about, okay? That's pretty much as simple as it gets. Check those numbers, make sure it fits those ranges, all right? So always check and make sure it fits. To help you out if you're struggling right now, I know this is new. Everything is based off the number before it. N can be a whole number of 1 to 7. That's it. L, whole number of 0 to n minus 1. Okay, so it's going to be from 0 to n minus 1. M sub L, whole number, negative L to positive L. And the spin quantum number can only be plus 1/2 or negative 1/2. That's the information you need whenever you're trying to verify, can these numbers exist? Can these set of quantum numbers exist or no? Okay?